Hi, everyone. So today I want to do a lesson on continuing talking about conservation of energy, but we're going to add in another kind of complication to what we've been looking at so far. So we've been discussing conservation of energy, and so just to review the equation that we had kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. Now, this works all the time. This is our equation. But what we've been simplifying in this equation is the fact that potential energy, what we've only been considering is potential energy from gravity, which we discussed was mgh. And this works fine, but there's actually other types of potential energy that an object can have. So you can have chemical potential energy, um, such as an explosive. When that chemical reaction happens, you have energy that's released into kinetic energy from that chemical potential energy. Another one that's really easy to see that we looked at in labs this year is spring potential energy, and that's what we're going to focus on today. So um, this potential energy term can really include any of these types of energies, any of these types of potentials, and one of which is PE spring. And so we're going to discuss what this potential energy is today, and do a couple examples to solve for that. So that's where we're starting at. So let's take a look at this example. So here we have a spring attached to a wall, and then we put a block on this, and let's say that this is on a frictionless surface, so the block can be free to slide to the right and to the left. Now, if you've ever played with like a slinky or another spring type thing, when you stretch that spring, it wants to return to its unstretched length, right? We did this in lab where we had the springs hanging and we hung a mass from it, we stretched the mass, and then the mass would oscillate up and down. And so in this example here, if this is the unstretched length, then what we're going to be doing is we're going to be stretching the string this way. We're going to be pulling the block to this point here, and this is our delta x, uh, how much it's stretched. And what happens when we release this? So I can hold it in this position, right? I can apply a force. I can grab this thing, and I can hold it right here. But as soon as I release it, everyone knows what's going to happen. It's the same thing as stretching a rubber band. When you release that, all the energy that was stored in this spring is now released, and what happens is the box starts to move this way as the spring applies a force to it, right here. And so if we looked at a free body diagram for this, we would have this spring force here, we'd have normal force, we'd have gravity downward. And so these two forces are going to cancel out, as long as, even if we have a little bit of friction here, it's still going to be pulled to the left, but we're going to ignore friction. And so what happens is this force that's pulling on this object is going to accelerate, and it's going to begin to oscillate back and forth. And so what we can see is that once it begins to move, it's going to have kinetic energy. So where did that kinetic energy come from? What we just talked about in like the pendulum lab was this pendulum oscillating from a state here across to a state here, and right, its energy was transferring between kinetic energy and potential energy as it reached its two peaks and went through the bottom. There's no gravity. There is gravity acting on this, but gravity is not doing any work on this, right? The force of gravity is downward. The delta x that this thing is moving is left and right. And so the amount of work that gravity does here is zero, which means that the energy has to come from somewhere else. Work is not applying any of this kinetic energy. And this energy is going to be coming from this spring being stretched. We're putting energy into the spring, and then the spring is going to put energy back into the box, which is going to cause it to move. What's cool about springs, though, is they actually return the energy in a similar way that gravity works as well. When we let this thing go, what's going to happen is it's going to oscillate this force is gonna apply uh, a a velocity to this thing. So it's going to start moving to the left uh, with some velocity. But what's going to happen is as it gets back to its unstretched length, so as the box returns later on to this point right here where it was unstretched, if we looked at the free body diagram here, we would just have normal force and gravity. The spring would not actually be acting on this object at this point in time because it's not stretched anymore. But it would, because it accelerated, it would still have a velocity. So it's still, let me actually do that. So it had an acceleration here, but its velocity was 0. So it began to accelerate to the left. So here, its velocity would be some number, and it would have an acceleration of 0. And then, so what's going to happen is it's going to continue here. And then as the spring compresses, let's say to a third point here, now if you think about squishing a spring, that spring wants to pop back out, right? You can think of those old the canned like peanuts with the fake spring snake inside of them. You pop the top off the the little snake pops out of the can, right? And that's because it's really it's spring loaded, right? That spring is compressed, so there's energy stored in there. As soon as you release it, the energy goes away, and it goes into the form of kinetic energy. And so again, my forces look like this. I still have my normal and gravity. Here, the spring was pulling this way, but in this example, the spring is pulling this way. And in the middle, the spring force is 0. And so what's going to happen is now my velocity goes to 0 at this point, but my acceleration is not 0 anymore. Now my acceleration is going in this direction. So we have an acceleration that's going to the left initially, then we have 0 acceleration as we go through the middle, and then we hit a point where we have rightward or positive acceleration as the object stops and then comes back. And so it's very similar to this pendulum idea of going back and forth. Okay, so that's what's happening here, and it's going to just continue to oscillate. Now, if there's friction involved, then friction will slowly bring this thing to rest, and it'll come to rest back at its unstretched length. Much like, as gravity works on this thing, there's friction that's eventually going to slow this thing down in terms of air resistance, and it'll eventually come to rest at the bottom, which we say is, its equilibrium position. Okay, so let's look at how we can you get some equations for this so we can solve some of these problems, and we're going to use Hooke's law. So if you'll remember from when we studied forces, Hooke's law was this force provided by a stretched or compressed spring. And it was very simply that the force of the spring would equal negative k delta x. The negative here is because the force of the spring always goes opposite of the displacement. If I displace it in the positive direction or pull it to the right, then the force of the spring wants to pull it back to the left. If I displace it in the negative direction, in other words, I compress the spring, then the force of the spring is to the right. And so this negative sign just opposes this delta x stretching. If I pull the spring apart, it's going to want to come back together. If I push the spring together, it's going to want to push back to equilibrium. So that's what the negative sign controls. K is what we called our spring constant, not to be confused with our winter constant or our fall constant. That was a joke. And just like in class, nobody laughs. And then here, this is our displacement. All right. And so this was measured in meters, and our spring constant was measured in newtons per meter. So we have this little relationship here. They multiply together, and we get a force in newtons. And so this force is what's guiding our spring potential energy. This force is what's doing the work. And if you'll recall, work is force times distance, and so you can imagine that it's going to be this force times some value of delta x, and so we can imagine that we're going to get a k delta x squared. Um, this formula is pretty interesting, and it's it has a term of 1/2 in here. So potential energy for a spring is it's always going to be positive. We're not going to have negative potential energy. We either have energy stored in that spring or we don't have energy stored in that spring, regardless of whether it's stretched or compressed. And so what we're going to have is we're going to have this delta x squared, our displacement value squared, times our spring constant. Because you can imagine our equation for work was force times distance. And this is my force that I'm monitoring. So I have k delta x, and then the distance is delta x. So I have this is k delta x, and this is delta x. So I get a k delta x squared. Now there's a factor of 1/2 that comes into play here. And this 1/2 comes in because this force is changing with delta x. It's not constant. As the spring becomes less stretched or less compressed, the force is weakened. And so we don't get k delta x squared, we get 1/2 k delta x squared. And a lot of the times we will just write this as, so PE spring equals 1/2 kx squared. So we won't write the delta x, but x is how far that string is stretched or compressed. Clean this up a little bit. K x squared. So k is our spring constant, and x is the amount stretched or compressed. All right. So hopefully that's good so far. This is another potential energy, and so it is another form of energy, and so the units of this are going to be in joules, or capital J. And so let's look at an example that uses this equation. All right, so here we have a spring has a spring constant of 440 newtons per meter. How much must this spring be stretched to store 25 joules of potential energy? So we want to spring load a spring so that it has enough energy to maybe push some object or apply a force to some object later on. And this could come, there's tons of applications to this, tons of engineering applications to this. So you know, we're just trying to get this much energy stored in a spring, and we know the spring constant of the spring that we're using is 440. So how much do we need to either stretch or compress this spring to store that energy? So let's imagine, here's our spring at its natural length, unstretched. And so what we want to look at is how far do we need to stretch this delta x if this thing is to have a potential energy of 25 joules. And so we can just use this equation here. PE potential energy of the spring is 1/2 times the spring constant times x squared. My spring potential is 25 joules. My spring constant is 440. newtons per meter, and then I get x squared. So what I'm going to do here is I'm going to multiply 1/2 by 440, you get 220, and then divide that over. So I'm going to have 25 divided by 220. And it might not be super clear how the units cancel here. But remember that our units of energy are a force times a distance. And so, 1 joule is 1 Newton times meter. And so if you're just looking from a unit standpoint, we have a joule is a Newton meter. And so we're going to get these newtons to cancel out here. And then I have a meter divided by a meter, which is meters squared. And so this becomes meters squared. And then when I take the square root of both sides here, that's going to go ahead and get rid of the squared component. And I'm going to be just left with units of meters once that goes away. And so I'm left with the answer that x equals 0.337 meters, or in other words, I need to stretch this spring 33.7 centimeters. And that will store 25 joules. All right, so let's look at a couple more examples on the next page. Here we have a 2 kilogram block moving with constant speed on a flat surface. When it reaches the end of an uncompressed spring, we're going to assume no friction here, just to simplify the calculations a little bit. So it reaches the end of an uncompressed spring. So basically what we have here is we have this block moving along a surface. It's moving at 10 meters per second. And it reaches the end of an uncompressed spring. So we have the spring like this. Maybe it's attached to a wall here. It's similar to how an elevator, at the bottom of the elevator shaft, if the cable were to break, then and this elevator were to fall, well, there's a braking system that's going to try to apply a frictional force this way up on the walls. But if it does get to the bottom of the elevator shaft, then there's these springs here that will basically catch this thing, compress it a little bit to try to break the fall a little bit. So similar idea here. We're gonna run this block into a spring and see how much the spring is compressed before the block comes to rest and reverses its motion. So what's going to end up happening here? Beautiful elevator. Is that the block is going to basically compress this spring all the way against the wall. So here it's uncompressed, here it's compressed, and we are looking for this value, how much it compresses this way. And then what's the speed of the block after the spring recoils? So if it, shoots back the other way, what would be the speed of it? Okay, so how do we solve something like this? Similar idea, but now we're going to be using conservation of energy. So not just solving for a spring potential, but we're going back to our kinetic energy plus potential energy equals kinetic energy final plus potential energy final. So in this example, it has kinetic energy as it reaches and impacts the spring. The spring is unstretched initially, and so there is no spring potential energy, and there's also no gravity potential energy. Because this thing, we're on a flat surface, we're not going downhill, uphill, anything like that. So we can ignore the gravitational potential energy. And since the spring is unstretched, there's no initial potential energy. The reason we get so we have 0 there because there's no gravity. And the spring is unstretched. For this final kinetic energy piece, what's going to happen, we want to look at it at this moment right here when it reaches a velocity of 0. So the final kinetic energy is going to be 0, and we're going to have a final spring energy that's stored in this spring here as it's stretched. And so I'm going to just write out my terms for kinetic energy initial. That's 1/2 mv squared. And this equals, that's 0, that's 0, potential energy final. Now we're not going to write mgh here. That would be gravitational potential energy. We're going to write our spring potential energy equation, 1/2 kx squared. Now notice that I can't cancel the mass like I was able to do with the other examples in the conservation of energy with gravity. I was able to cancel out mass very easily. But in this case, since we're looking at potential energy of a spring, it does not depend on the mass of the block that's impacting it, just the spring constant. And so we can't just cancel out the mass. In other words, when we're looking at gravity, mass doesn't matter. But when we're looking at springs, the mass does matter. Certainly, if I have a heavier block, this spring is going to compress more than if I have a lighter block. And so I can't cancel out the masses because the mass does matter. Luckily, they tell us that the block weighs 2 kilograms, so I can just plug that into my left-hand side of the equation. My initial speed is 10, and I got that from here. And then the spring constant is 2,000 newtons per meter. So that's going to be my K value. And I'm left with x squared. 1/2 and 2 cancel out, so I've got 10 on this side. I've got 1/2 and 2,000, so I've got 1,000 on this side. X squared. I can cancel out one of the zeros, and then 1 divided by 100 is 0.01, and then, oh, I forgot the squared. So this should be 100. Yeah, these cancel out. That's 100. So this will be 0.1 equals x squared. And so that means that x equals 0.316 meters, or 31 centimeters. That's how much this is going to compress whenever the block runs into it. What is the speed of the block after the spring recoils? So this is, you might think, oh, we got to set up another equation. We got to look at once the spring gets back to its unstretched length here. How fast is the block moving this way? But there's a really important thing here. Since we're assuming no friction, then there's no energy loss here. And so once the spring is unstretched and has reached its initial length again, and our potential energy of our spring goes back to 0, our kinetic energy returns to what it was initially. And so my velocity would also be 10 meters per second, but in the opposite direction. So my speed would be 10 meters per second, just as it was before it hit the block. So we would say energy is conserved. All right, so hopefully that's making sense so far. I've got 2 more examples to look at that involve gravity as well. So we're going to get a little bit more complicated here. All right. So here we have a 50 kilogram crate on top of a 5 meter tall ramp. The crate slides down the frictionless ramp and comes in contact with a horizontal spring, which has a spring constant of 2 times 10 to the 4th newtons per meter. How much will the spring compress in bringing the crate to rest? So this is what we're looking at. You can imagine, some ramp here, and we have a box on the top of it. The box starts to slide down the ramp. At the bottom, we want to cushion the fall of this box, and so we put a spring here, something compressible. And this doesn't necessarily have to be like a metal spring. You guys can think of like even something like that has some ability to compress. So these types of calculations, what's good about a spring is that the energy is conserved in terms of it being stored into the spring. We can measure it based on how much it compresses, but the idea is still the same in terms of like even like airbags and things like that, to cushion impact. The main difference there is the energy is not conserved. In those cases, the energy is given off when the object changes shape. So, for example, the crumple zone in your car. If your car is going along and it runs into another car, that car will compress, and that changes energy from what it from that kinetic energy into another form of energy. But since that crumple zone isn't going to spring back, the energy is going into some other form, which essentially is reshaping that metal, and that keeps the passengers a little bit more safe. So this idea of energy conservation still applies in those cases. It's just being transformed to different types of energy. Um, but it's a similar idea in terms of the amount that you can compress it is the amount of energy that can basically be changed out. So if you have a larger crumple zone, then you can reduce the amount of impact that the passenger might feel. Anyway, so here we go. We got this box. It's going to slide down the hill this way, and it's going to hit this spring here. And what we're going to be left with is a compressed spring, some amount delta x. All right, and what we want to know in this example is how much will it compress? So what is this delta x going to be? Now, a couple notes. They gave us this ramp is 5 meters tall, and we know it's frictionless. We know it's starting with a velocity of 0, and we know our spring constant k is 2 times 10 to the 4th newtons per meter. All right, and so we're just going to do another conservation of energy equation. K initial plus P initial equals KE final plus PE final. We're starting with that. Now, here's what's interesting about this. I actually have both a gravitational potential energy here and a spring potential energy here. So I'm actually going to have initial potential energy and final potential energy, but we're going to use different equations for these. All right. KE initial is going to be 0 because velocity is initial is 0. And as it goes down the ramp, collides with the spring, and then the crate comes to rest here, velocity is also going to be 0 there. So my final kinetic energy is also going to be 0. So my initial potential energy is going to be mgh. It's all gravity, no spring potential. So this is all gravitation. And this is all spring. So I have mgh equals 1/2 kx squared. There's no gravitational potential energy here because my height is 0. All right, and so I can plug in my numbers, 50, 9.8, and 5, and that's going to equal 1/2. K is 2 times 10 to the 4th, and then x squared is what I'm looking for. All right, and so I can plug this into my calculator at this point. Multiply these 3 together, multiply those 2 together, divide it over, and then finally take the square root, and 0.49 meters, about 50 centimeters is going to be the amount of compression. All right, and this brings us to our final example for today. So here we have a 20 kilogram box resting against a compressed spring. So now we're looking at the end of that problem. When the spring is released, the box approaches a ramp which leads to a platform 2 meters above the ground. If the spring has a spring constant of 1700 newtons per meter and is compressed 75 centimeters, how fast will the box be moving when it reaches the top of the platform above? So essentially, we have the reverse of what we have. Basically, we have a spring-loaded launching device here. All right, it's compressed, and there's some box which we can think of as our projectile here. And then there's a ramp, and it gets to the top. And what we want to know is, as it goes up this ramp, how fast is it going to be moving when it gets here? All right. So when this releases, what's going to happen is this spring is going to unstretch, and it's going to give the box a velocity that's going to lead it up the ramp, and it's going to lose some energy as it goes up, and then it's going to reach its height and have some velocity. So here we go. Conservation of energy, name of the game. Ke initial plus P initial equals Ke final plus Pe final. Same idea as last problem. Here, our kinetic energy initial, as this thing is released from rest, its velocity is 0, so I don't have a kinetic energy. I also have a height of 0. So I don't have a gravitational potential energy, but I do have a compressed amount of spring. It says the spring is compressed 75 centimeters. So I have an initial spring potential. So this is all spring. All right, and then after this thing is released, it flies up the ramp and it reaches this point here. And it's going to have a kinetic energy because it's still going to be moving, but it's also going to have a potential energy, but not because of the spring. When it gets to this point here, so here delta x is negative 75. Doesn't really matter, positive or negative. But here delta x would be 0. It's not stretched or compressed at all, and so the potential energy would be all gravitation here. No spring. And so my initial potential energy for spring would be 1/2 kx squared. My kinetic energy would be 1/2 mv final squared. And then my PE final would be all gravity, no spring, and so it would be mgh. And so now I have to plug in chug 1/2. K is 1700 here. X is how far it's compressed, 75 centimeters. Note that this is 0.75 meters. We want this to be in meters. 0.75. Our box mass is 20. So 20, our V finals, what we're looking for. And 20, 9.8, and our height, which is given as 2 meters. All right, so now I've got all my numbers. I just got to plug it into the calculator. What I would do is I'd solve for this number first, get a number for there, get a number for there. That's 10. Subtract this over, and then divide by 10. And then finally take the square root. And doing so will result in the answer 2.93 meters per second. All right, so there you have it. All different examples of potential energy for a spring. So we have a spring-loaded problem where an object's being launched. We have a spring catching an object as it's flying into it. We have a spring rebounding an object as it catches it and then launches it back the other direction. So here, that's our main equation. And remember, we're always going back to this idea here. But we can have two types of potential energy, gravity or spring. All right, so I'm going to have you guys work on a problem set. over the next couple days. Well, obviously you have the weekend, but next Monday and Tuesday we'll be working on a problem set. So feel free to drop by office hours too. Monday, Wednesday, Friday, from 1:30 to 2. I'd love to see some of you guys answer any questions you have. Um, and if you just want to drop in and say hello, I wouldn't mind that. So yeah, I will talk to you later. I hope you have a great weekend, and until next time, I'll see you.